All right. Let's go. So last time we were looking at the ratio test, we looked at these two examples. Let's actually go through them. So example A. So first of all, this is something that you could use the alternating series test on, just so you know. That is not going to be as comprehensive as the ratio test, and we'll talk about in what sense that is. But just so you know, you could use alternating series test here. But what you would obtain from that, if it converges by this test, it is conditional convergence, and that, so you should just be aware of that. So had you done this with the alternating series test, you might get convergence, you might not, but if you do get a convergence, it would be what we call conditional convergence, and I'm going to remind you about that as we move on. The ratio test, though, actually tells you about absolute convergence, which we know is different from conditional convergence. So, especially if absolute convergence is what you're after, you would choose the ratio test over the alternating series test for this guy. So let's actually do it with the ratio test, just to see how things would look. So, how does the ratio test go? What do? We set up some limit, right? What was the limit?
The limit is n approaches infinity of, so like n plus, like that, if that's a of n, then a of n plus 1 over a of n.
A of n plus 1 over a of n in absolute values. So you set up that equals L, and based on what value you get for L, you can make some conclusion. So if your L is less than 1, it converges absolutely. If your L is bigger than 1, diverges. If your L equals 1, no conclusion. Right? So that was the ratio test. So if this guy here, this is my, that guy is my AN, I'm just going to set this limit up. So notice here I would have L is equal to the limit as n approaches infinity of. Now I'm going to write the minus 1 to the n here, but just so you know, in general, once you have doing the ratio test, you throw absolute values, you can actually ignore that part. But let's throw in n plus 1 over 2 to the n plus 1. Now of course, instead of dividing that by n, we can just multiply by the reciprocal. So that's going to be 2 to the n over minus 1 to the n. So this part here is just, it's your 1 over an that I'm multiplying by. This part here is 1 over n. Okay. Now, for this one, probably not particularly important to do this, but if things get too complicated, it's going to be hard to see how things are going to simplify sometimes. So what I like to do is I like to group the similar kind of terms together. So these alternating signs, I'll put them together. Then I have the guys that are polynomials, I'll put them together. Then I have the guys that are exponentials, I would put them together. Right. So I just kind of separate everyone, group all the like guys together. That way you just see what simplifies easier. So you know, all of this cancels into that. You know, that the 2 to the n cancels all of that. So pretty much now you have the limit as n approaches infinity of minus n plus 1 over n over 2n. Now, at this point, the absolute value of the negative, it's just going to kill the negative anyway, so you can actually ignore that. But pretty much something like this is literally always going to happen. So the truth is you could have ignored from the very beginning. You could have ignored this part. You didn't have to put it. You could have ignored this part. You didn't need it. At the end of the day, the absolute values are going to kill whatever negatives are there. And now you just take this limit. Now what's that limit?
1/2.
It's 1/2. Now what you'll notice about 1/2 is it's less than 1. So what that means is now you'll be able to say the series converges. More than that, you'll be able to say it converges absolutely. Absolutely it converges. That's it. That's the ratio test. You set up this limit with absolute values around it. Depending on what the limit does, you can make the conclusion. Less than 1 converges absolutely. Bigger than 1 diverges. 1, no conclusion. And remember, if your original series is just the series of a rational function, it's always going to end up in this case, so don't even try the ratio test in that case. But here's one situation which you can try the ratio test. Questions on this? Okay. Now let's look at B. And look at this guy here. What can you tell me about that guy?
So, well, let's do the ratio test.
You could. Let's not though, first. You saw that random guy show up. What could you tell me about it? We're going to do the ratio test, but your first impressions here.
It's an alternating series?
It's alternating. Can you tell me whether you think it's going to converge or diverge?
Probably goes to infinity because factorials are really fast.
Right. You'll notice here by test for divergence, if you look at n factorial over e to the n, that's a factorial versus an exponential. Factorials they grow faster. This guy actually approaches infinity, which is not 0. So it actually diverges. Right? Now, I'm going to go through the motions and do this by ratio test. But if this guy showed up on a test, you shouldn't be doing ratio tests. You should just notice, hey, that's going to diverge. Right? You're just going to say, that limit approaches infinity, it diverges. Right? So just so you know. So for sure this diverges. And again, that's because this is a relationship you always need to remember. Logs grow slower than polynomials, grow slower than exponentials, grow slower than factorials, go slower than the variable exponentials. Right? So we have a guy like this versus a guy like that. Guys like this are much bigger as you're going off to infinity. So that's going off to infinity. So I know it's going to diverge. But let's go through the motions anyway, just so you can kind of see how it would actually, because I actually wanted to see how like a factorial would behave under this kind of scheme. Let's go through the motions. So you're going to set up L equals the limit of an plus 1 over an, as I mentioned here. And again, you can kind of be sloppy here. It is always going to be n approaches infinity, so I don't even have to write it. So right here, just forget about the minus 1 to the n part. It's not going to matter. The absolute value is going to kill it anyway. So I'm just going to plug in n plus 1s everywhere. And then I'm going to multiply by the reciprocal of this guy. So, had I not thought of test for divergence, which you really should be thinking of test for divergence, and I just ran in with the ratio test, here's what it would look like. And what does that look like? Well, now this guy's going to cancel that. How does So if I have n plus 1 factorial and I divide by n factorial, what does that guy behave like?
That gives you n plus 1.
It just gives you n plus 1, right? So what you're going to notice is that n plus 1 factorial, well that just means n plus 1 times n minus 1 times n minus 2, going all the way down to 3 times 2 times 1. But then you realize this part here, well that's just n factorial. So n plus 1 factorial is just n plus 1 times n factorial. So the n factorials, the factorial parts just actually cancel out. The n factorial is going to cancel that guy out. And so this leaves us with the limit of n plus 1 over e. And you take that limit as n approaches infinity. E is a constant. That goes off to infinity. Well, that's bigger than 1. Right? Really bigger than 1. So this tells you the series diverges. Which, yes, we knew all along, but I wanted to introduce this kind of trick to you. This is one of the reasons why this particular test, the ratio test, is super convenient for factorials, because it allows you to cancel them out and obtain something that's not a factorial at the end of the day. So, ratio test, one of the situations in which we like to use the ratio test is with whenever I see a factorial around. I would tend to want to use the ratio test, provided that my test for divergence didn't already tell me the thing diverged. If I wasn't sure if it converged or diverged, I see a factorial, ratio test is going to be like the first thing I think about after divergence, test for divergence. One more main test to tell you about, then talk about absolute convergence again, I guess. So there's another test. What is this, test number 9 now or something? It's called the root test. It involves a root. It's called the nth root. So given any series n, if we set L, so we're going to compute some other limit now. It's going to be the limit as n approaches infinity, obviously. But now what we're going to do is we're going to take the nth root of an in absolute values. So it's called the root test. You're going to take a root. We may conclude based on the following. If L is less than 1, the series converges absolutely. Again, you know it's going to be absolute because you're actually throwing in absolute values around here, so your signs aren't going to matter. If your L is larger than 1, the series diverges. The conclusion looks just like the ratio test, and there's another connection that I'm going to mention. Diverges. Again, L equals 1, no conclusion. You might also notice that the terms here are allowed to be 0 because you can't have 0 under a radical. That's not going to be a problem. In the ratio test, you can't have any of the terms being 0 because you actually divide by them. But that's the root test. Now, as may be suggested by the nth root, this test is useful when we have, this test is useful if we have exponentials, right? Particularly if you realize that your an just looks like some other sequence raised to like an nth power, or like a constant times n power, you can just use the nth root to get rid of that nth power and make a conclusion based on this. Sometimes you actually seeing what it would look like without the nth power is actually going to make your life a lot easier. So that's called the root test. Another thing that you should note here, we're going to realize that there are going to be some problems where we might have to do several tests, or you might run in and try to do a test with a problem and you might realize, oh, this test doesn't quite work, I can't get it to work for this problem, let me try something else, right? That might happen. One thing you should note with the root test is that the ratio and root tests give analogous conclusions. Okay? They're going to make the same kind of conclusion. So let's say I went in and I tried to do a problem with the ratio test, right? And it didn't work out. Then I'm like, okay, so I have to use some other test now. The root test should not be one of the other tests you think about. If the ratio test is inconclusive, the root test will also be inconclusive, and vice versa. They're going to kind of tell you the same sort of thing. So wherever you can get them both to work, they're going to kind of tell you exactly the same thing. So if this guy if the ratio test can't work out, then this guy's not going to work out. So it means if this guy's not going to work out, that guy's not going to work out. So if you try this and it doesn't work, don't try that. And if you try the ratio test and it doesn't work, don't try this. You have to try a whole completely different test. The ratio test and the root test, they're very close together. Their conclusions even look the same because they kind of behave the same way. And yeah, that's one thing. So do a silly example here. See something like that? Now, it should kind of stand out to you. So first of all, you're going to realize that that limit approaches 0, so it's not going to, you probably won't diverge, at least you're not sure, so you're going to try something else. But the fact that it has that nth power there kind of makes you think of, hey, if I could get rid of that nth power, I could talk about that guy a little bit easier. With the nth power, that's kind of annoying. So what you can do is just set up your L to be the limit of the nth root of the absolute value, 2n plus 7 over 7n minus 3 to the nth power. What's going to happen? This guy's going to cancel that guy. We're going to end up with a limit of now 2n plus 7 over 7n minus 3. So values. What's that limit?
2 over 7.
That's 2 over 7. Now 2 over 7 is less than 1. So in fact, what you can conclude is the series converges. Moreover, the series converges absolutely. That's basically the ratio test. So like I said, each test individually, I mean, it's probably not going to be hard to work them out. The challenge here is just like with integrals, is that I'm not going to tell you what tests you should use in advance. So you're going to have to be able to look at a series and know what approach you want to take. And I'm going to talk about strategy, just like I spoke about integration strategy with this guy, series test strategies. But before that, I just want to mention the 10th thing, absolute convergence. Your book talks about this thing called the absolute convergence test. It's not really a test though, specifically. And this just means testing whether this guy converges using some other test, really. Right. So it's not really a test unto itself. It's just kind of maybe like a directive that you would use, right? So absolute convergence is you really caring about whether the series with absolute values will converge around it. And so if this guy converges by some prior test, then we say the original series without the absolute values converges absolutely. As I mentioned last time, absolute convergence is super important for calculus because guys that converge but don't converge absolutely, you can actually change their value by rearranging the order in which you're adding things. And that kind of messes up a lot of things we want to do in calculus, like distribute integrals or derivatives across a sum. If you want to do that across an infinite sum, the guy better converge absolutely. Otherwise, no dice, it's not going to work out. So, absolute convergence is important to be able to do calculus with series, right? Otherwise, calculus isn't going to understand the thing you're looking at. The series might as well be gibberish if it converges conditionally. Second, there are going to be times where I'm going to specifically ask you about absolute convergence. You will be asked about whether, so there will be problems where I don't just ask you if something converges or diverges, I'll ask you whether the series converges absolutely, conditionally, or diverges, right? Now, if the question is so phrased, right? That means when you tell me that it converges, I want you to specify whether it does so absolutely or conditionally. Now, and in that case, what you want to do is you want to check absolute convergence first. In this case, check absolute convergence first. So you're going to if you see like a -1 to the n, just ignore it. Whatever it is, just make sure, just look at it as if all the terms were positive. Would it still converge? The thing is, if you check conditional convergence first and it converges, you will still have to check absolute convergence because it's possible to converge without the absolute values but not with them. So if you go conditionally first, so like if I see a -1 to the n in my series and I go alternating series test, right? Just because I see the -1 to the n. But this is the question. After you do the alternating series test, you'll have to do another test where you ignore the alternating series test. And that's just doubling your work. If you just directly went with something else, like the root test or the ratio test, what would happen is you would get absolute convergence right off the bat. Once you have absolute convergence, you automatically have conditional convergence. You don't have to check anything else, right? So if you have to talk about absolute convergence and conditionally convergent, check absolute first. If this guy works out, it covers that guy. But this guy does not necessarily cover that guy. This can work where that doesn't work. But if this works, that definitely works also. So you go here first. Ignore your negative signs, make sure, pretend everyone's positive. Check that first. If that diverges, then you check conditional, right? So if converges absolutely, you're done, right? If this diverges, then check conditional. If it converges now, conditional convergence. Otherwise, now it diverges. So you check absolute convergence. If you get that, you're done. You pretty much say, oh, it converges absolutely. Suppose you try that and it didn't work out. You can't immediately say it diverges. You will then check conditional convergence. If that works out, now you conclude converges conditionally. And then if that doesn't work out, then you go to diverge. So you have to go through like 3 phases here. Check absolute, does it work? No. Check conditional, does that work? No. Then it diverges. But you always want to start with the absolute convergence because this covers that, but that doesn't cover that.
If all the terms are just positive to begin with, and you kind of can jump from not
Yeah,
being-
then any convergence there is absolute convergence by default.
But then if it doesn't absolutely converge, you can kind of jump to divergent, right?
Right.
Okay.
Because in that sense, you're kind of checking conditional and absolute at the same time because the series, even with absolute values, is just himself.
Right.
So, yes. But there are guys where you don't want to be too sloppy with it. So for example, the alternating harmonic. Simple example, but very instructive one. That guy, right? So if I ask you, does this converge absolutely, does it converge conditionally, or does it diverge? If you just run in and check it as is, using the alternating series test, you'll get converges, right? But you have to be aware that that just means conditional convergence. So you can't just conclude, oh, it converges. You'll have to specifically say, oh, I know it conditionally converges. But then in addition to that, now you have to throw absolute values around it. That's going to transform him into 1 over n. That's the harmonic series, and then you know diverges. So this is a guy that converges conditionally, right? He does not converge absolutely. If you look at someone like this, oh, well, like we did a previous example. -1 to the n of n over 2 to the n. That guy converged absolutely. Now you could have gone in with the alternating series test, you would get convergence, but then it's conditional. You'd have to do something else where you ignore this to check for absolute, right? So might as well you just check for absolute in the first place. And yeah, okay. That being said, let's actually talk about how to approach these guys, because I pretty much tell you all the tests, the convergent tests that you're going to apply. So strategy for testing convergence. So I'm going to tell you guys a strategy. It's actually important. What I notice in grading the test is that people don't follow the strategies anymore. So I noticed a very common thing that would happen, like most people did this. They encountered some integral where they tried to complete the square. Almost every paper I read tried to complete the square at some point to do an integral. Completing the square was not required at any point in that test. Right? So I saw people like trying to complete the square and do a trig sub. I'm like, a regular substitution would have worked. Why would you go to a trig sub? Now you're just making your life harder, and then it didn't work out at the end of the day. Right? The strategy is important. It will save you from wasting time and going down a path that you just don't need to go down. So I mentioned in an email that you should try to go over your test before looking at my solutions, but when you look at my solutions, you're going to realize the integrals were actually pretty straightforward. Regular substitution, nothing crazy. There was a partial fractions, no trig sub anywhere. But I saw almost everyone at some point try to complete the square of a denominator and try a trig sub. I'm like, why would your mind go there? It's not in the strategy. You would think substitution first. The strategies are going to help you not go down the wrong path. So pay attention to the strategy. So first of all, there's a 0th step to the strategy. you'll notice that out of all the convergence tests I told you, 2 of them specifically tell you exactly what the series converges to. This was the telescoping series. And geometric series. They tell you not only that something converges or not, they tell you what something converges to, which is quite strange. You can actually find the exact answer. What does that mean for you? If in a problem I tell you, hey, tell me what this series converges to, it means it's one of these 2 guys. It's definitely one of those 2 guys. You won't use the ratio test, you won't use the root test, you won't use alternate, you won't use any of the other tests, because the other tests don't tell you what something converges to. It only tells you if something converges. So if there's any point where I require you, hey, tell me what the actual answer is, it means that you should only be thinking of 2 things, right? So if a problem asks state what a series converges to, use one of these. Now, which one of these? Well, the geometric series has a very specific form, right? So you're going to look for that form. Is it geometric? If no, then telescoping is what you should be looking at. So remember, the geometric series is the guys that look like AR to the n, if your n starts from 0. Or if your n starts from 1, it's AR to the n minus 1, right? So if I say, okay, the following series are convergent. Tell me what they converge to. If I ask you a question like that, it's this or that. So the first thing you're going to look for, does it look like this? Because the geometric series has a very specific form. Telescoping series has no specific form. So I'm going to look, is it geometric, the thing that I'm looking at? If yes, you just do that formula. You know what it's going to converge to. It converges to A over 1 minus R. If it's not geometric, then you're going to be like, oh, it must be telescoping then, because you asked me exactly what it converges to. So it must be telescoping. And the go-to technique there is going to be to do like a partial fractions, where you split it up into several fractions and they cancel each other out. So that's like a step 0. That's just dependent on the kind of problem I would ask. Now, most of the time the kind of problem I would ask is something like, tell me if the series converges absolutely or conditionally or it diverges, right? Now, when that is the general type problem, that's where you go into the actual steps. So, the first thing you're going to try is try test for divergence. The first thing you want to do is see, does this even converge in the first place? Am I going to waste my time even doing a test? In theory, by now you guys should be so familiar with limits, you could just at a glance kind of tell whether a limit is going to converge or not. Or at the very least, you'll be able to tell at a glance, is this limit going to be like an indeterminate form? Okay, what would L'Hopital's rule tell you? And chances are you'll be able to like even do most of that work in your head. It's very quick to test for, and it's going to be worth it. Even if you get the limit, so this one tells you that if limit of an is not 0, then series diverges, right? So that's what this tells you. It does not tell you about convergence, it tells you about divergence only. Diverges. Right? So now let's say you check a limit, you do test for divergence and you realize that the limit is 0, then yeah, you wasted your time, but it's not going to take a lot of time. It'll only take a few seconds. And if you don't do it, you might take a much longer time finding out the thing diverged than if you were to just do this quick check in the first place. So test for divergence, one of the first things you're going to look for all the time. The second thing you're going to look for is you're going to look for series that have specific forms. So you'll notice, for example, when I told you about, the ratio test or the root test, it works on any series, right? But there are some specific forms, like the geometric is a specific form. right? So you're looking for things that look a very specific way. Alternating series have a specific form. They'll usually have like a -1 to the n, right? So you're going to try to spot things like that. Are there specific forms that I want to do? The geometric and the alternating series test is a specific form. The p-series test is also a specific form, 1/n to the p. I think those are all the specific forms you would have here. So geometric, alternating, and p-series, right? These guys all have a specific form, which with a little algebra you should be able to maneuver a series into this form. So again, it's one of those things you're going to look for because you kind of know exactly how they look. It's not totally arbitrary. There's actually a specific characteristic that you should be able to spot with your eyes right off the bat. So you'll tend to want to look for those next. Because the moment you recognize one of them, then it's easy peasy. It's easy to move on from there. So you're going to want to try specific forms. 3. So if I ask you what something converges to specifically, it's going to be geometric or telescoping, one of the two. Assuming that I didn't ask you a question like that, test for divergence is the first thing you're going to think about. The next thing you're going to do, look for guys that look a specific way. These are the geometric, the alternating, and the p-series. Those guys, you'll be able to spot them right off the bat. They'll just look different from everyone else. Now, if an, so test for convergence of, I'm just using an as a generic series. If an is a rational function, I would say use one of the comparison. Right? The ratio and the root tests are never going to work for rational functions. Don't waste your time. Use one of the comparison theorems. Notes here, usually you compare to a p-series. Right? Just keep the biggest powers, ignore all the lower powers. And notice that when you ignore all the lower powers, if you can tell who would be bigger or smaller, that's going to be good. But if you can't tell, if the p-series is larger or smaller than the original, then you use the limit comparison test. Otherwise, you're going to use the regular comparison test. Right? Sometimes it's going to be obvious, right? If you make a denominator smaller, the fraction gets bigger, and if the p-series that you compare that to converges, you know the original converges. If you make the denominator bigger, the fraction will get smaller, and if that's the p-series you're looking at, and that guy diverges, the original guy. So there are going to be times where the inequality, you're going to know exactly how it's supposed to turn, and you can just use the direct comparison theory. Now, if by ignoring the lower guys, you get something where you're not sure if it's bigger or smaller, don't waste time trying to figure out if it's bigger or smaller. Just actually go to the limit comparison test. And what else? So there are also, if an includes factorials and or exponentials, try the ratio test. So I would say you would do again, like integrals, you would do these first three in order. But the remaining steps I'm telling you about is in no particular order. It just depends on what you're spotting. So you would try these, but if those don't work and you notice it's a rational function, a comparison test is what you should be thinking. In no particular order here. If you just happen to spot a rational function, comparison. If you know, if the guy you want to compare to is bigger or smaller, use direct comparison. If you don't know, use limit comparison. If what you're looking at has factorials and or exponentials, the ratio test is probably going to be your best bet. That guy's also going to be nice because he's going to tell you about absolute convergence right away. 5. If an includes exponentials, especially if you realize that your an is just some other guy to the n, or something to like the kn plus b, anything like that, right? Anything that has a linear power of n, that's going to be really convenient for the root test, right? Because first of all, you can factor a guy off, and then the nth root is going to kill that, and it's going to give you a constant power at the end of the day. And k, and the plus b is going to be a little bit sketchier. But anything that looks like that, stuff into a constant times n power, you're probably going to think the root test. Use root test. And again, remember what I said, ratio and root test, they are very similar in their conclusions. So if you try this and it doesn't work out, don't try that. It's gonna be they'll both be inconclusive at the same time. Now, probably something that's going to be a little bit harder to spot, only a little. Not great with integration, it's going to be a lot harder to spot, but maybe you can spot it. If an is easily, by easily I just mean you can spot a technique right away to do it, integrable. And of course, goes without saying, but an is positive, decreasing, and continuous when thought of as a function. Try the integral test. So this allows you to do an improper integral to judge how your series behaves. If the improper integral converges, the series is going to converge. If the improper integral diverges, the series diverges. 7. If asked about absolute convergence, check this first before checking conditional convergence. And that's the basic strategy. Let me leave you guys with some examples to actually try this out. So try these out for next time. And by the way, there are problems like this that were on the bonus to your test. You can even try retry those problems. So, example. State whether the following converges absolutely, conditionally, or diverges. Cosine squared n plus 1 over n squared plus 1. Minus 1 to the n, cosine of n factorial over n to the n. Minus 1 to the n, n over n plus 1 to the n. And the last one, d minus 1 to the n over ln of the radical of n plus 1. So try those. Use the strategy, see if you can get through those. We'll pick up with those next time. We'll probably also start power series next time, maybe. Probably want to talk about approximating series next time, but yeah, try these. And I'll see you next week.
Bless you.
All right, so your next quiz is just going to be on pretty much series. Yeah. So ask you to do a bunch of series.
So the quiz will just be like testing for whether divergers or convergers. Maybe
Yeah.
like where convergers to like will we ask us where convergers?
I might, but if I do, it's definitely going to be geometric.
What about you?
So I might ask you a problem like that as well as a general problem like this.
Have a good day.
All right.